Hi, my name is Omar Alejandro Alvarez Gonzaga, and I want to talk about a part of the work we have done in my PhD research at Instituto Politécnico Nacional, and it's related with organic solar cells and density functional theory. In 2006, Marcus Scharber and his coworkers proved several organic solar cells, where the active layer was composed of a donor semiconductor polymer and a molecular acceptor known as PCBM. From these solar cells, they obtain their open circuit voltage, the highest occupied molecular orbital, or HOMO, of the polymers, and the lowest unoccupied molecular orbital, or LUMO, of the PCBM. By means of a linear fit, they found a very simple relation between the open circuit voltage and the difference between the HOMO energy of the polymer and the LUMO energy of the PCBM, with the reciprocal of the electronic charge E as the slope and minus 0.3 volts an additive constant. So, in order to study this correlation, it was made a geometry optimization of the PCBM and several oligomers from 11 polymers presented in the mentioned work, using density functional theory or DFT. Particularly, from these calculations, we take the monomers with just one polymer unit, the tetramers with 4 polymer units, and PCBM obtained to calculate their HOMO and LUMO energy values. We ordered Schaber's polymers respect to their HOMO energies, from the highest value to the lowest value, and we label it in that order from P1 to P11. All the calculations were performed for each isolated structure using ADF program developed by software and for chemistry and materials. Geometry optimization was carried out with the Purdue-Eschenhoff generalized gradient approximation as the exchange and correlation potential with Gram dispersion, while electronic properties were carried out with Beckett tree parameters Legend-Park grid functional. In both cases, were used a triple zeta parallelized Slater base, and considering all the atomic orbital functions. All calculated energy values were plotted together with Scharber values to compare. Almost all monomer values in red squares are below to experimental values, labeled with green crosses, while the tremors that correspond to blue circles are almost above the Scharber's ones. Also, calculated PCVM LUMO in black line is greater than Scharber's in green dashed line. Respect to the last one, we have found experimental values that fit very well with ours. The problem is with polymer HOMO energy values that just not fit well, but even they don't follow Scharber's tendency. However, our values are below PCVM calculated energy, as it is expected, and they agree with the known behavior of this kind of systems, which HOMO energies are higher for longer chains. Particularly, P10 shows a poor variation from monomer to tetramer values, in contrast with other Theophyne derivatives like P4 or P5, which have the greatest variations. Then, we observed the main difference was the twist angle between units, which is 0 in planar P4 and P5 and near 90 degrees in P10. In view of these results, we did two fast calculations as a benchmark to understand this behavior. We performed, with the same level of theory, geometry optimization of thiophene and benzene dimers, and from these optimized structures, we rotate one unit respect to the other to obtain for each dimmer structures with angles of 0, 30, 60, 90, 120, 150, and 180 degrees, calculating their HOMO and LUMO energy values. As a result, for both dimmers, it's observed that the lowest HOMO-LUMO energy gap is obtained with planar structures, while the highest one, which is very near to monomer value, is obtained with perpendicular units, with symmetric higher values from 0 degrees and 180 degrees to 19 degrees. Also, HOMO and LUMO energies decrease and increase, respectively, as angle get closer to 90 degrees. In the case of HOMO, its value in 19 degrees is basically the same as monomer. The difference between planar and perpendicular HOMO-LUMO gap in both cases is around 1.3 electronvolts. Observing this tendency, we obtained from each optimized tetramer the conjugational length, which is associated with the physical length of the polymer, and the average twist angle between the units of each tetramer. Additionally, We calculated the difference between the tetramer and the monomer HOMO energies and calling it as delta HOMO. For each tetramer was plotted delta HOMO with the conjugation length on one hand and with the average twist angle on the other hand. The tetramers was ordered upward respect to conjugation length and twist angle, respectively. It can be observed that there is a tendency that for higher conjugation length values, there are lower difference between monomer and tetramer HOMO energies, except for P10. However, for twist angle, the same tendency is more pronounced, where P10 has one of the highest angle values and the lowest value for delta HOMO. We can conclude that high values in twist angle between units in a semiconductor polymer reduce changes in HOMO energy values respect to its unit, even if polymer has a high conjugation length. Also, differences between Scharber's values and the values we obtained could be related to their degree of planarity in real systems, which are part of an organic solar cell. As a next step, we will perform a optimization of Scharber's polymers with periodic conditions instead of a high, but limited, number of units in order to obtain more realistic values with lower computational cost compared with the last mentioned. Finally, we want to thank the CONACYT for the scholarship awarded and Instituto Politécnico Nacional for the CIF research resources and BEIFI scholarship.